Alright, we're going to look at why this idea of a t-distribution, isn't it bad enough having a chi-square and a normal distribution. Now we've got this idea of a t-distribution. Okay, so in chapter 4, that's what we want to look at. You'll see the spreadsheet behind me there. That's where we're going to do some simulations to look at this. And the way we're going to see is why a t-distribution, we're going to look at confidence intervals. So from previous work, we did a 95% confidence interval. And I'll try to keep an eye on the screen, on the computer screen, as I write, because I had to start this over because I lost the computer screen from no activity with the mouse, and I didn't realize it. So you all would have been looking at the dark. But so we want this 95% confidence interval, and remember with p hat we assumed that we could think of this was a normal distribution, and we know that 95% of our data from a normal distribution is within plus or minus about two standard deviations. So 95% of our data are within plus or minus about 2. Now the actual number is 1.96 sigma, so 1.96, about 2, and so we use that number to build our confidence interval. We said, oh, okay, we're going to take our p hat minus 1.96 times the standard error up to p hat plus 1.96 times the standard error. And what we did with that interval was, if we were taking data and getting a proportion, then that actual proportion could be somewhere between 0 and 1, and we'll just say that it's about there, that was the actual proportion. So that was our real value of p, not a p-value in the sense of a hypothesis test, but a proportion p. And we made a confidence interval. We got a p hat somewhere, maybe that p hat was about there, and we built a confidence interval around that p hat. And what we hoped was that, yeah, it was a close enough number that when we built this confidence interval up here, the real answer p was somewhere in there. And the way I drew it here, yeah, it's in there. And then, well, if we did it again, we'd get a different confidence interval, but we would hope that, again, the real answer is in there. Well, if we do enough of these, we just keep going down. Well, actually, there will be some that won't have p in them, the actual value, and then many others that will. But again, we come down here. Oh, here's another one that doesn't. Overall, what we would expect is, if we're using a 95% confidence interval, we expect 95% of the intervals contain p. Okay, so that's what a 95% confidence interval means. And so now when we go to, instead of just proportions, now proportions are a type of mean, but when we expand it to just numerical averages, in this case we do the same idea. We have x bar, and then we'll do plus or minus our number based on the confidence interval. So that's the question, is what number goes there, and then times our standard error. And again, for normal, we use 1.96. Well, what we're going to see is that actually Oh, visor add in 10 seconds. Well, we're about done with this, so perfect. Actually, we're going to need a number generally that's not 1.96. So there's your visor add. Okay, so let's look at our actual simulations here. And so let's talk about what I did for the simulation. And so as you look at this, what I did was I just generated 4 normal distribution numbers. And for that normal distribution, I'll double click here. This is a little small probably on your screen. We can make this bigger. So you see I did a normal inverse. I took a random number, and this 0, 1 says, well, I'm sampling from a standard normal distribution. And as you look at some of these numbers, you know, you see a 0.1, here's some negative numbers and so forth. Now, I did not take the average of all of these numbers, nor the standard deviation of all of these numbers. If I did, the overall average of all of the numbers I did here, I have 4,000 numbers because I took a sample of 4, so those 4. I did that 1,000 times. And so I took that sample of 4, then I got its mean, its sample mean, x bar, and this one happened to be negative 0.2. But again, if I did all of these and took their average, all 4,000, it'd probably be very, very close to 0. And then I also found the standard error, which is just, I did the standard deviation divided by the square root of n. Now the way I found n was I just counted how many things were here, and I just did that because I wanted to make copies of this particular sheet and expand this number. But all it's doing is saying take the square root of 4 because there are 4 things there. So I took the standard deviation of those items and then divided by the square root of n to get the standard error. So here's x bar, here's standard error, and what I did was I generated a lower bound. So this is my z lower bound, or z is the standard normal distribution. So I assumed a 95% confidence interval with a normal distribution, and so here notice this C, where is it, A2, this A2, it is looking over here at this 1.96. So there's our number of standard deviations or standard errors. So here's x bar C5, and then minus our 1.96 times the standard error here of 0.687, and then for the upper bound I just did a plus. Okay, so I did my mean minus about 2 times the standard error, and then my mean plus about 2 times the standard error. Okay, so I did that, and then I checked over here, did this interval contain 0, because 0 is the real mean, and it did, so I put a 1. And then here again, if you look at these two data, here's my interval for this one, minus 0.223 to 0.4. It again contains 0, but notice this interval, this confidence interval, does not contain 0, and so I put a 0 here. So I did that all the way down for all 1,000 rows, and I counted up. Here I summed up all the ones, or I just counted basically all the ones, and notice that out of 1,000 of these runs, actually only 843 had confidence intervals containing 0. That's a problem. It should be 950. Now again, we allow for some randomness here. I can update this. If I hit enter there, it updated, and I got different numbers, and now it's 856, but that is definitely nowhere near 950. Now, so what I did then was I changed the 1.96 to this number, 3.18 something or other, right? Now, what this is it is the number of standard errors I should use if I have a sample size of 4. Now, the way we designate that, or what we call that, is a t-distribution of 3 degrees of freedom. So we just take our 4 data points and we say, well, let's take 1 minus that, and that's our degrees of freedom. We don't really need to get into why we designate it that way, but in the end we do. If it's 4 data points, we call it 3 degrees of freedom. If it's 10 data points, we would call it 9 degrees of freedom, and so forth. But so I had Excel look up the number that this is, and it says, no, don't use 1.96, use 3.18. And so I use that, and that's what I did in these 2 cells. So here I did that same thing. I took X bar and then minus, but this time instead of the 1.96, I used the 3.18. So I made the confidence interval wider because I used a bigger number here to multiply by, but then D5 is still the standard error. So in our formula for a confidence interval, all I did was change the multiplier, the 1.96 to 3.182, but that 3.182 is based on a t-distribution with 3 degrees of freedom. And again, I did that for the upper bound. I checked that same way. And notice when I count that up, instead, I didn't get exactly 950. I got 959. Okay, but very close to the 950 I would expect. And again, I can, do something like recalculate, and wow, so here let's freeze frame this baby because it is exactly 950. And so we see, just sort of from this sample size of 4, that a much better number for this sample size is a number a little bit bigger than 3 than a number right around 2. Now, what happens is that number, though, changes as the sample size changes. So here we have a sample size of 9, so I have x1 through x9, but I did the same thing. I found the average, I found the standard error, I took that 1.96 and I made a lower bound and an upper bound for my confidence intervals for that, decided whether my 0 was inside that confidence interval, and it either was or wasn't. And notice, we're doing a little better. We got 924 this time, as opposed to with the sample size of 4, we only had 851. So it's getting closer to the 950. But if you look up here, the number we really should use, I see I have a typo. Let me fix that right now. This is 8 degrees of freedom. So 8 degrees of freedom because I have 9 items. That number is 2.3 compared to the around 3.2 we had before. So you see that number's coming down, and it's getting closer to 1.96, but it's not quite 1.96. And we can see the difference we have here is, again, this number a moment ago, before I changed the 3 to an 8 up here, and that's just text, that didn't do anything to the formula. It said 948, so it was almost exactly 950. This one, though, again, you see it's too low. And the reason it's too low is that's too narrow a number. We need a wider confidence interval. We need 2.3, not 1.96. But with this bigger sample, sample size 9, we are getting closer to the normal distribution. And now if we go to a sample size of 25, and again, see, I forgot to change that, so this is degrees of freedom of 24. And when we have degrees of freedom of 24, a minute ago we had, what, 954. Now I just changed it and it's 945. But see, we're right around the 950 mark, and I can recalculate this thing. So I recalculate. Wow, there it was clear up to 961, and this one looks pretty good. Well, this number is always going to be smaller than that one because that number is bigger than that. If this number's smaller, that number is smaller. So for the same data, it's just a narrower confidence interval due to the smaller number, and that's just true with confidence intervals in general. Whatever that multiplier is, if I make the multiplier bigger, I make the confidence interval bigger. And so that multiplier is based on what kind of confidence I want. And all of these are 95%. And so now you see we're getting really close. I mean, this is 1.96. This is 2.06. We're only off by, what, 0.1. And we see that the numbers are getting much, much closer together. Again, we could recalculate and, whoops, there we go, recalculate. And here we're at 954, 944. So you see we're getting close here in this number, but it's really not quite there. It's a little small because the 1.96 is a little smaller than 2.06. This number is always going to be just a little too small for our 95% confidence interval. Now, as a general rule, though, once you hit 30, statisticians pretty much say, hey, it is okay to go with the 1.96 Z number instead of the T distributions number. And sure, that's fine. Again, we're pretty, even at 25, we are really close to the 1.96. If in general you were just using the number 2 as opposed to 1.96, well, yeah, then we're even closer. This is definitely very close to 2. And if we take it up to a sample size of 36, now here I want to change my degrees of freedom again to 35. Now we're clear down to 2.03, and once again, if in general I was using a number like 2 instead of 1.96, I'm getting really close. And notice these two numbers are very close together. So this is a sample size of 36. So this simulation is really showing that yeah, by the time I get somewhere around 30, 40, maybe 50, who knows, but somewhere in there, I am definitely close enough with my T distribution number to the normal distribution number that, sure, why not? I can just use a normal distribution. It's close enough. And again, like I say, the rule of thumb for a 95% confidence or an alpha of 0.05 is a number about 2, and both of these numbers are about 2. And actually, this one is closer to 2 than that one is. And so you see, in that way, by the time we hit somewhere around 30, here we're at 36. By the time we hit something like that, then we really are doing fine if we just assume the normal distribution. But for smaller sample sizes, we need to use a T distribution. And again, we see that very evident here with a sample size of 4. Those numbers are very, very different. This number being about 2, this number being bigger than 3. And so for small samples, we really need to use the T distribution, not the standard normal distribution. And if you're using a spreadsheet, something like that, it doesn't really matter. You just have to remember to use the T command instead of normal command. And we'll definitely be looking at that with some of our other work. So that's why a T distribution, why we have that in there. Why we're not doing it just to make people's lives miserable. Although that is a perk, I suppose, but it is, it's really about the fact that you don't get the right answer if you assume a normal distribution. You need to use a different distribution to get the right answer, or at least about the right answer for any given sample. All right, so that does it for this recording.